Hello, everybody. Welcome back. I'm sorry for the delay. We had a problem with our Van de Graaff generator this morning, and we're just trying to do a plan B here. Today, we're going to talk about voltage. And I think all of us have some understanding of voltage in the sense that we know that we're supposed to be afraid of it. You know, if someone tells you, there's 120 volts at that outlet there, you're not supposed to stick stuff in there. Your parents taught you that, right? And that's because this idea of voltage is very, very connected to the idea of energy. And you remember from Physics 105 that energy is simply the capacity to mess stuff up, the capacity to do damage. And the more energy you got, the more you should be afraid of it, okay? And so our gut tells us that if something says, whoa, there's 2,000 volts there, we give it some distance, okay? Another warning, and that is, you remember in Physics 105 when we got to the section on energy, that the exam was a doubled humped distribution. We had a bunch of A's and we had a bunch of C's. And it wasn't really how well you understood energy. It was how well you could do algebra, okay? And these problems dealing with energy and again with voltage very quickly become algebra problems. And for some of us, that's good news. You're excited about that. Some of you are not so excited, and you know which camp you're in, okay? So I'm just giving you fair warning here. Let's start by taking attendance. I will get you started. Okay, now you can click.
But I actually he didn't spell one skied one time, but I'm stupid.
So yesterday I was like, oh
wow. Dude, that was fun.
Okay, last call.
I don't have any.
Okay. Before we talk about voltage, let me just talk about that last tutorial. And you remember on page 3 of that tutorial, we had this situation where there were two charged balls, A and B, and it was really important that they be glued to the table and that they be non-conductor, because we were going to bring a third ball that was charged, ball C, and we didn't want that ball C to change the problem. Well, it's clear that those first two balls, A and B, had to be glued to the table, because otherwise they would fly off the table like that. Yeah, that's coming out of your tuition. Okay, we spared no expense. Bringing in that ball C, if A and B aren't glued down to the table, they could fly off the table and change the whole problem. But they also have to be non-conductors. I know that I can charge a metal ball. We've done that with the Van de Graaff. But once I charge that metal ball, the electrons are free to swim wherever they're happy. And so if I bring ball C into the room, if it happens to be positive, all of the electrons are going to swim around to get closer to it. If I bring a ball C in that's negative, all the electrons are going to swim around to the back of A and B to get away from it. That changes the problem. With a non-conductor, like a plastic or rubber, if I put the charge on that ball, it stays where I put it. It doesn't go swimming around, okay? So that's why you needed it to be a non-conductor. Now, the question on this page was, when I bring that third ball C in, and I bring it in to try to measure the field due to A and B, are these the field lines that are important? Or are these the field lines that are important? Tell your neighbor which it is, left or right.
Let's see.
Yeah, that one. This one, it makes actually compare anything to the yeah, you don't measure the effects of the. Oh.
Okay,
Bird sleep. What's that? You say. When to like like yes.
I hope,
But then
I really hope that everyone said to their neighbor, this is the field that matters.
I don't know.
This is the field that matters. And the bottom line is, charge C doesn't push on himself. Charge C is being pushed on by A and B. A and B are the Klingons. They're the ones setting up the field, and this is the field due to A and B. Okay, when we set up our equations, you remember that two-step dance that we went through, there were three different ways to set up the electric field. If my source was a point, I use Coulomb's law at the top, but I could also have a sheet of charge or two sheets, one positive and one negative, in which case I would use those other formulas. Regardless of how I found that E field, doesn't matter. I can plug it into this formula to find the thing I really care about, which is the force on the Captain Kirk, the test charge. And the key here is that that electric field is created by the other charges, all the charges except the test charge that's feeling it, that's being pushed. Okay, so if I go back here, this is the field due to A and B. And if I put charge C right there, it would get pushed that way. If I put charge C there, it would get pushed that way. If I put charge C there, it would get pushed that way, assuming that charge C was a positive charge. Whereas this field, this would be the field that a fourth charge would see, a charge D. If I brought a charge D into the room, A, B, and C would be pushing on it. And then this field would be the one I cared about. Check that your neighbor understood page 3 of that tutorial. Slap them if they didn't.
Or like the homework.
Someone.
Okay.
Yeah.
Last day we had a problem with our projector there, and it turns out the projector was completely bad, so we got a different one. But we were talking about the electroscope, and we said that it was a very simple device to measure whether we had charge or not. And this simple one just has two pieces of foil that hang down next to each other. And when I charge up the electroscope, some of it gets on this foil and they spread out. Now, I've got a more sophisticated case, electroscope, and that looks like this. And the important parts of this electroscope are this metal top and this metal bar that comes down the middle. And then also this yellow bar is also metal. And you see that if I put charge on this, let me do that. I'm going to take this rubber rod and charge it up and touch the top here. You see that I get some of the charge on the yellow bar that's free to rotate, and some of the charge on the one that's stationary, and they repel each other. Now, because this rubber rod is a non-conductor, the only charge that went over was the charge from where I touched it. If I want more charge to be transferred, I've got to scrape it off like peanut butter because the charge is stuck where it's put. And there you see I get a big deflection there. Now I can get rid of that charge on the electroscope by touching it to a large conductor like the Greg, okay? And then I get rid of that charge. Now I'm going to do a demo that was first done by Michael Faraday. And this demo is called Faraday's Bucket. And I start with a neutral bucket. I know it's neutral because I'm touching it. And touching that, everything's neutral. Touching this, I'm just touching everything, okay? And so what I'm going to do, we know how this works. We spray electrons on the rubber band. The rubber band takes the electrons up to the top. We take the electrons off of the rubber band and they congregate on this metal ball. I then give them the opportunity to go down this wire to the inside of that bucket. I'm dumping electrons inside the bucket, and I'm going to dump a lot because I'm generous. I'm going to just dump all sorts of electrons into that bucket. Okay. Now, that's enough. Now I'm going to, I felt a spark. That's not a good sign. Okay. This may not work because of that spark. We'll give it a try. I put all those electrons on the inside there. So if I go looking for those electrons, what I find is nothing. They're not there. Well, where did they go? Well, let's look out here. They're not there. Okay, so I felt that spark and that was it. Let's do better. Be better, Greg. Be better. Now, in case this doesn't work, I sent you a video of a time when it did work very well. I sent you the link. Okay. Now, again, inside I'll get nothing, but if I go outside, I should get something. Oh, okay, people. There it was. Now, again, let me prove to you that there's nothing on the inside. Nothing. Okay. Okay, let me turn that off. So what does that mean, Greg? Why do I care whether the charge is on the inside of a bucket or the outside of a bucket? Well, you care because there might come a day when you are stuck in a lightning storm. And the fact that this charge has to be on the outside is something that could change, could save your life. Okay, we call this electromagnetic shielding, and all of the excess charge ends up on the outside of a metal, leaving the electric field inside the metal zero. That's what we found last day. Now, if you're in a lightning storm, the best thing you can do is get into your car, close the doors. Some people think it's the rubber tires that are protecting you, and they will if your tires are 1 mile thick. I don't know about you, but my tires are not that thick. What's protecting you is we call it a Faraday cage, the metal around you. Now, at the Boston Museum of Science, they have the original Van de Graaff machine that Professor Van de Graaff used at MIT. And when he retired, they put it on a barge and floated it down to the to the museum. And what they do with that now is they have a bird cage made out of metal, and they put in that bird cage a graduate student because they're expendable. Okay. And then what they do is they charge up this Van de Graaff generator, and they lift up the bird cage until they get huge lightning strikes on that metal cage, bird cage. Now, my young children and I, we love to go there. We were just a block away from that. We had a family pass. And so we'd go all the time to watch this happen. And the grad students, what they would do is they would put their hand on the inside of the cage, right where the lightning was striking, to make it clear that the charge was staying on the outside. Now, there was one grad student who was so much better than the others. We loved him because he did not put his hand on the cage. He put his tongue on the cage, right there where the lightning was striking. And my kids were just, oh yeah, that's what I want to do when I grow up. Yeah. Okay. At least they didn't get a motorcycle. Help. Okay. Questions on that? Yes.
Outside.
She asked, what if I own a Corvette which has a fiberglass body? You're toast. What was your question really?
Outside, not just like your house, half of it.
Oh, it's on the very surface of the outside. Yeah, it's not, oh, did they make that bar thick enough? You know, it could be really thin. It's just on the outside surface. Okay. Let's talk about voltage. It turns out it takes 30,000 volts to throw a spark through 1 centimeter of dry air. So yeah, okay. So clearly that was more than 30,000 volts, hundreds of millions of volts, okay. And what's going on there, we will understand in a month when we talk about induction and why that big arc was there. But for now, we just recognize that that's a whole lot of voltage. And why did that arc rise up while you were watching it? Why? Anyone have an idea? Really?
But does it repel each other?
What's that?
Because it repels each other? Because it repels?
No, doesn't repel. We've punched a hole through the air, ionizing a path that then becomes the easiest path for the charge to flow through. Okay. Why is that path going up? Yes, sir.
Super hot.
Yeah, it's super hot. It's heating up the air around it. The air around it is rising, taking that path of least resistance with it. And that's why the arc went up like that. Okay. Now, what I want you to see, what I desperately want you to see, is that if you can understand a boulder falling off a cliff, you can understand the one and only voltage problem that exists in the whole universe. Is that hopeful? Hopeful? Now, to make that connection, I have a pretest here, and I need my helpers. Where are my helpers on this side? Thank you. Thank you. Helpers on the other side. The left-hand helpers.
Very cool.
Are you indeed left-handed? Okay, I need another left-hand helper. Okay. Look alive.
Carry a chain around you the whole time.
You get nothing.
Like super long, just wrapping around yourself.
Get some of yours.
What can I say? Spring.
You. Oh, you were, that's. They don't.
Good.
Loaves and fishes, loaves and fishes. Just give us lunch and we'll pick up on the other side.
Just not, I can't.
They might make it in. Oh, there's one more that one I can.
Thank you. Oh, my goodness. You got to get yourself. You know what they say when you're in an airline and it's. Put on your own mouth.
I don't think the rest is.
What?
Oh. Yes, and they're still. Yeah, how much people say they're the best, they're still under.
Gotta be around you. It probably hurts from that, right?
We play a 5 week.
No, you got to do it.
Gonna win it all.
Okay,
Easy.
really quick, it's a very easy pre-test. It's more about 105 than 106. Do it. You can do this. Quick like a bunny.
Yeah, but they should have a lot of options. Not bad on that. So. Hundred times. Interesting.
Here you go, sir. Excuse me, sir. You're welcome. It did what?
Faraday's bucket opening creates dipole.
No, it's because those electrons are repelling each other, and the furthest they can get away from each other is on the outside of the bucket. Okay, folks, I know that many of you are not done, maybe most of you, but we started class 5 minutes late. My bad. So let's just work through this together. Okay, let's work through this together. You remember that when we were in Physics 105, we thought of energy as being in buckets. And we had a bucket for kinetic energy because that was always positive. We either had it or we didn't. We could put it in a bucket. We had this gravitational potential energy. And as long as we chose the lowest point in our problem as 0, that was always positive. And so we either had it or we didn't, and we threw it in the bucket. And then we added those two buckets together to get what we call total mechanical energy. Sometimes it's called mechanical energy, sometimes it's called total energy. In this case, that boulder is at the bottom of the cliff and it's not moving, so there's nothing in the kinetic bucket. It's at the bottom of the cliff, so there's no gravitational energy. I'm not afraid of that boulder. And so there's no total energy. Until we do Werk on it. And remember, Werk is just work, but in physics. I call it Werk. I call it Werk because it's different than what you did on the farm. And I want to make that distinction. But you remember that Werk had a very complicated definition. It was positive force times the distance if you're pushing in the direction it's going. It was negative force times the distance if you were pushing opposite the direction it was going. And it was actually 0 if you were pushing perpendicular. And that's what made it so different from work on the farm. Okay, you could have a big bale of hay on your shoulder, walk a mile across a level field. You did no Werk, but you'd be expected to be paid for it. Okay? Now, if my friend Rand wants to take that boulder where it doesn't want to go, it doesn't want to be at the top of the cliff, it wants to be at the bottom of the cliff. If he takes it to the top of the cliff, he's going to have to do positive Werk because he's pushing in the upward direction and it's moving in the upward direction. But how much of that, how much Werk does it do? Well, if I look at a free body diagram, if I assume that gravity is 10 newtons for each kilogram, it's 9.8, we're going to call it 10, then the weight of that boulder is going to be 100 newtons. Now, if I want Rand to lift that up at a slow, constant velocity and put it on top of the cliff, how hard should he push? Harder than 100, equal to 100, or less than 100? Tell your neighbor real quick.
Hard.
Okay. If we believe in Newton's second law, and if it's moving with 0 acceleration, Rand has to push with exactly 100 newtons. Now he has to push a little bit harder to get it started, a little bit less to get it stopped at the top, but on average, he's pushing with 100 newtons for a distance of 12 meters. And so the Werk, I just multiplied the 100 newtons by the 12 meters, and I get 1,200 joules of positive Werk. Now you remember, Werk is what changes total energy. So if Rand does 1,200 joules of Werk, positive Werk, that means we fill up the total energy bucket by 1,200 joules. But the boulder's still not moving, so the kinetic bucket is still empty. And that means all 1,200 joules has to be in that gravitational bucket. Okay? And that's how we got our formula for the gravitational bucket. We did Werk in such a way that we could only fill up one bucket. Hold that thought. That's going to be important in a few minutes. Now, suppose that Rand just taps that boulder, making it fall off the cliff. I'm saying that was very irresponsible. That's a terrible thing to do. Someone could have gotten hurt. Don't do that. But that's what he did. Okay? Now, what happens here is that the total energy stays 1,200 joules. He didn't do any Werk. He just tapped it and went home. Okay, no Verk is done, so no energy is lost. Now, when it gets to the bottom of the cliff, the potential energy bucket is empty. And that means all of the energy is in the kinetic energy bucket. Okay, and so if I know how much energy was in that potential energy bucket, I can figure out how fast it's going at the bottom of the cliff. And that, my friends, is the only voltage problem in the world. That's what you're going to solve 20 times on your homework, 5 times on the exam. I'm going to dress it up so that it looks different each time. You're not going to recognize it. But that's the only problem there is. A falling boulder. A falling boulder. Okay? Now, let's look at the electric case. In the gravitational case, Rand fights the gravitational field, essentially cocking a gravitational spring to store that energy. Okay? Well, let's look at the electric case where I've got a positive sheet here and a negative sheet here. I know what the field looks like in between those plates. It's uniform. The field lines go from the positive to the negative, and they're parallel, so that means that my electric field is everywhere the same. Boring, okay? Well, that looks familiar, okay? If I look at this like that, that's the top of the cliff, that's the bottom of the cliff, and the gravitational field, remember, goes from the top of the cliff to the bottom of the cliff. Here it's an electric field instead of a gravitational field. But it's the same problem, okay? And if I take a boulder, no, that's not a boulder. That's a 1 Coulomb charge. But it's like the boulder. That 1 Coulomb charge, where does it want to be? It wants to be near which plate? Yeah, it wants to be next to the negative plate. It's attracted to the negative plate. What it doesn't want to do is be near the positive plate. So this is the bottom of the cliff. That's the top of the cliff. And if I try to move that from A to B, I'm going to have to do positive Verk. I'm going to have to push against that electric field to get that 1 Coulomb from A to B. Just like Rand pushed the boulder against the gravitational field to the top of the cliff. And in both cases, we're storing energy, potential energy. In the case of the cliff, it was gravitational potential energy. In this case, it's electric potential energy, but it's still energy. What I'm doing with my hand here is cocking an electric spring, storing that energy. Now, you remember back in Physics 105, we had the grand high Verk energy theorem. And what this theorem said is that the energy in the morning is always equal to the energy at night, except when it isn't. And it usually isn't, okay? Whenever we do Verk, we change the energy. Now, that formula helped us a great deal in Physics 105. But that form of it's not so useful in Physics 106. In these electrical problems, we usually don't know what the initial energy is, and we also don't care. We also don't really know what the final energy is, and we don't care. What we do care about is the change in energy. So let me show you a better form of this equation. If I take that initial energy and subtract it from both sides, final minus initial, we call the change in energy. The change in energy. And what this says is that external Verk changes the energy. Okay? Now, I can change that energy different ways. I can either change the energy by changing the kinetic energy, or the gravitational energy, or the electric potential energy. Just like changing your bank balance can be done by either adding money to your checking account, or adding it to your savings account, or adding it to your CD account, or all three at once. Okay, this side here would be a deposit or a withdrawal. That changes your overall, and then I can make those changes in the different accounts, and they have to add up to the withdrawal or the deposit. See if your neighbor understands that equation. It's speaking to his soul or her soul.
Not like large from. Five.
Okay.
Yeah.
Now, for most of the problems, like 90% of the problems on the homework, you're dealing with little tiny particles like protons and electrons, whose masses are so small that this gravitational bucket just never amounts to anything. And so for 90% of the problems, we're just going to neglect that bucket. And all we worry about is the kinetic energy bucket and the potential energy bucket. Okay. Now, there are a few problems down the road where we charge up a heavy ball. It's got a mass of 2 kilograms. And then you have to worry about this gravitational bucket. We'll get there. You know, don't worry about it now. Don't worry about it now. Now, if I use that formula, again, with the kinetic energy bucket and the electric potential energy bucket, I can get a gut level feeling for what this electric potential energy is. But I have to do something special. I have to push that 1 coulomb from rest slowly across at constant velocity and then bring it to a stop. If I start with it stopped and I end with it stopped, then this change in kinetic energy is 0. And I get rid of it. And now I have a way of measuring how much electric potential energy I stored, how much energy I stored when I cocked the electric spring. I just measure how much work I had to do, and that's how much energy I stored. Okay? Now, just suppose, I'm pulling this out of my left ear. Suppose I move that from A to B and it costs me 100 joules of air, positive air. Okay? Everyone see that? I had to do 100 joules of air. Well, what if instead of taking 1 coulomb from A to B, I took 2 coulombs? How much air would I have to do? Is your gut screaming out 200? Yeah. Because that 2 coulombs is going to be pushed by the electric field twice as hard as the 1 coulomb, and I'm going to have to fight twice as hard to get it across from A to B. So I'm going to have to do 200 joules of work. Well, that's how I measured the energy that I stored. That means I stored from, when I moved that 2 coulombs from A to B, I stored 200 joules. Well, what if I had brought 5 coulombs across? How much energy would I store? Shout it out. 500 joules. What about 10 coulombs? 1,000 joules. Well, this one's a little different. -1 coulomb. Let's think about that for a minute. -1 coulomb doesn't want to be next to this negative plate. It yearns to be next to this positive plate. So if I just let it go, it's going to go racing across there. But remember, I have to make it go from rest to rest. And so what I have to do to bring it across slowly is I have to push this way while I'm moving it from A to B. What kind of work am I doing? That's negative work, -100 joules. Okay. Now, how do I write this in general? Well, in general, I would say I have to do 100 joules of work for each 1 coulomb. And then if I multiply that by how many coulombs I take across from A to B, that will tell me how much energy I stored in that potential energy bucket. Okay? Now, what we call this, we call that the change in voltage from A to B. And we're always worried about the change in voltage from one point A to another point B. That's what matters, the change in voltage. Now, I have to apologize on behalf of a whole lot of physicists that came before me, and a whole lot of my colleagues that are still teaching it this way. A lot of my colleagues are calling this potential. And that's a problem. In the 40 years I've been teaching this, I find that potential sounds a whole lot like potential energy. And if I make the mistake of calling this potential, my students get all sorts of confused. And so my friend Jeff Adams and I took a blood oath years ago that we would never, ever, ever call that potential. We would always call it voltage. And indeed, if I'm being careful, I'm always going to call it the change in voltage from A to B. But sometimes I get sloppy and I just call it the voltage. Okay, it's the change in voltage from A to B. Now, I hope you see, and we've been here before, that this is a rate. That's how much energy I store for 1 coulomb going from A to B. That's like the price of a gallon of gas. If I know how much 1 gallon costs, I can tell you how much 10 gallons cost. I just multiply the cost of 1 gallon by 10. And that's what we're doing here. That's how much energy I store when I bring 1 coulomb across. If I want to know how much energy I store when I bring some different amount, I just scale it. Now, we call that the electric voltage. Okay, so summary. The change in voltage from A to B is 2 things. It's a change in potential energy if I bring 1 coulomb from A to B. But if I bring that 1 coulomb from A to B in a special way, namely from rest to rest, it's also equal to the Verk that I would have to do to take that 1 coulomb from A to B. And that's something I can easily measure. Check that your neighbor understands what voltage is. If not, do what you do.
Talk about this.
You know, there are a lot of universities in the world where I wouldn't have found 15 hymnals in the back room. That made all the difference there. We were getting arcing from that little wooden box, but the hymnals, they didn't arc. Okay. Now, which point, A or B, is at the higher electric voltage? What do you think, A or B? Shout it out. B, yeah. If the change in voltage from A to B is a positive quantity, that means I gotta have a bigger number at B, okay, a bigger number at B. And so it's going to look like this. And that's something you can take to the bank. The voltage is always, every stinking time, going to be higher near the positive plate. Always going to be lower near the negative plate. Always, 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 always. Okay? Now, protons want to go this way. They want to go downhill, just like boulders want to fall downhill. And you know, so far the analogy is holding pretty good. Boulders are positive mass, protons are positive charge. They both fall downhill. We get into trouble when we get to negative charges like electrons. We'll get there. We'll get there. Okay? If I say that the change in voltage from A to B is 100 joules for each coulomb, and I call that 100 volts to honor a dead physicist, well, what that tells me is that if I have 600 volts here, I have to have 500 volts there. But if I have 800 volts there, I have 900 volts there. And both of those situations give me exactly the same physics. I never care really about the absolute value at A or the absolute value at B. It's always the difference that matters. just like with problems with elevation, with boulders falling off cliffs. Okay, whether I call this floor 0 height or whether I call sea level 0 and say this is at 4,800, you know, when I drop a ball in the room, I get the same physics regardless of which numbers I'm using. It's only the difference in elevation that matters. Okay. Now, I promised you that there was only one voltage problem in the universe. And this is it. Okay. You release a proton at B, and you want to know how fast it's going when it gets to A. It's the boulder problem. You drop a boulder from the top of the cliff, how fast is it going right before it hits the bottom of the cliff? That's the one voltage problem. So let's solve it together. Okay, let's solve it together. If the voltage difference from A to B is plus 100 joules for each coulomb, what's it going to be from B to A? Because that's what the proton's going. It's going from B to A. Okay, so what would that be? Negative 100, negative 100. Okay, now, again, that's a rate. That's just a gimmick to get me what I really care about. What I really care about is the change in electric potential energy from B to A. And to do that, I take the change in voltage. That's how much change I'd get for 1 coulomb. And then I multiply it by how many coulombs I actually take from A to B. I'm sorry, from B to A. Sorry, I misspoke. From B to A. Now, I know the charge on a proton is the elementary charge, 1.6 times 10 to the minus 19. And so I plug that in, and I multiply by negative 100, and I get this number here, negative 1.6 times 10 to the minus 17. Joules. Joules. Notice that the voltage is in joules for each coulomb, but the potential energy is an energy, and it's in joules. In joules. Okay? That's how much potential energy that proton has to give up as it goes from B to A. Now, what happens to the kinetic energy? Well, this is the picture I want you to see every time you close your eyes to go to sleep at night. Okay, this is the last thing I want you to see before you start dreaming. Okay, it's a zero-sum game. Whatever I lose in this bucket, I gain in that bucket. Okay, again, Rand just kicked the boulder, did no verk, and it fell off the cliff. Gravitational potential turned into kinetic. Here we just let the proton go, just let it go. Did no verk. And so that means all the potential energy goes into kinetic energy. Okay, so remember the change in potential energy was negative 1.6 times 10 to the minus 17. The negative sign means that bucket is draining. Well, the kinetic energy bucket must be filling. So its change must be a positive 1.6 times 10 to the minus 17 joules. And since that proton started from rest with 0 kinetic energy, that change has to be the final kinetic energy. And since I know the mass of a proton, that'll be on the front page of the exam, I can solve for that speed and get a number that nobody cares about in the room. Okay? Check that your neighbor understood what just went down there. That's the one voltage problem in the universe that we'll solve over and over again.
Now.
Stand by, we have to go plug it back.
You'll pick the time. But we'll see how fast it is. You have to know this.
Okay. It's just like the boulder problem. You tell me how high the cliff is and what the mass of that boulder is. I will tell you how fast it's going at the bottom of the cliff. And in the gravitational case, you don't even need to tell me the math. But with the electric case, we need the charge. Okay? Now, again, this is my summary slide. The change in voltage from A to B is the change in electric potential energy if I take +1 Coulomb from A to B. And if I do it in a way that it starts at rest and finishes at rest, I can also say it's how much Werk I had to do to take it from A to B. Now, let's do a kind of a visual to make sure that we're all on the bus. That's a much younger Greg. That was back when I was alive. Okay. If I have a bowling ball right above my head, I'm not concerned. It has very low gravitational potential energy. Energy being the capacity to hurt me. Okay. Likewise, if I have a positive test charge right here next to this negative plate, it has low electric potential energy. It's at the bottom of the cliff. Okay, it's where it's at its happy place, where it wants to be. Now, if a hand does positive Werk on the bowling ball, fighting the gravitational field, cocking that gravitational spring, we get to a place of higher gravitational potential energy. And we say that the change in gravitational potential energy has been positive. When your bank account has a positive change, it filled up. It filled up. Okay. Likewise, by pushing this test charge to the top of its cliff, to a place where it doesn't want to be, fighting the electric field as we go, we bring it to a place of higher electric potential energy. And the change in electric potential energy is positive, We store that energy. Well, then what? Well, then we let them go. And now no work is being done. And so we keep the energy, but not in the same bucket. All of a sudden, that energy that was in the potential bucket goes into the kinetic bucket. And we can figure out how fast the bowling ball's going. We can figure out how fast the charge is going. And that is the one problem that we'll be solving. Okay? Now, where does the kinetic energy come from? Again, I want you to always see that picture right there. It's a zero-sum game. The only way I can fill this bucket is to empty that bucket. Are there questions so far? Questions? Do a quick buddy check. Talk to your neighbor. See if your neighbor's okay.
Got it.
No child left behind, people. No child left behind.
I think that
It's like the school lunches or like.
Okay. Now, I hope this is feeling familiar, that we've been here before. You remember that the relationship between the electric force and the electric field was through this equation here. And now we find that the relationship between the electric potential energy and the electric voltage looks similar. In both cases, we get a gut level understanding of what these things mean by setting our test charge equal to +1 Coulomb. If I do that, then the force is the same size as the electric field. And that tells me at a gut level what electric field is. It's the force I would have if I reached into my pocket and if I pulled out 1 Coulomb and if I put it at the X. Well, the same thing's true with voltage. What is voltage? Well, it's how much Werk I would have to do if I reached into my pocket and if I pulled out a +1 Coulomb and if I push that 1 Coulomb from A to B. That is what the voltage is, storing that electric potential energy. Okay? Now, I suggested that maybe electrons are what mess everything up in this analogy. And that's because electrons don't act like boulders. Not at all. Not at all. If I look at the electric field between those plates, that's always going to point from the positive plate to the negative plate, regardless of whether I'm pushing on an electron or not. It's independent of the test charge, independent of the Kapton curve. Okay? Now, the force on that electron, since it's a negative charge, is going to be opposite the electric field. And so that electron is going to want to race to the left. Well, which point, A or B, is at the higher electric voltage? Well, it's always higher near the positive plate. It's still going to be point B. But now that electron is racing towards uphill. Okay? If we think of voltage as elevation, electrons want to move uphill, want to go to higher voltage, not to lower voltage. And that messes up the whole analogy with the gravitational boulder. Now, if we redefine what we mean by down, we can make it so that everything falls down. Well, let me show you how I do that. With elevation, my gravitational field always points from high elevation to low elevation. And if I let go of a boulder at the top of the cliff, it speeds up as it goes towards the bottom of the cliff. By speeding up, its change in kinetic energy is positive. Well, that positive change has to come from a negative change in the potential energy bucket. It's a zero-sum game. And in this case, the change in elevation, the change in height, is negative. It's going downhill. Now, if I have a region of high voltage and a region of low voltage, just like with elevation, the electric field always goes from the high voltage to the low voltage. Always. Always. No exceptions. Okay? And if we deal with a positive charge like a proton, it speeds up in that same direction. It's speeding up so the change in kinetic energy is positive. That energy has to come from somewhere. So the electric potential energy bucket empties, its change is negative. And if you're going from 250 volts to 150 volts, your change in voltage is going to be negative. If that was money, you'd say, I'm losing money. Okay? Here comes the wrinkle. A negative charge like an electron is going to speed up the other way. Well, it's still speeding up, so the change in kinetic energy is still positive. That's got to come from somewhere, so the change in electric potential energy is still negative. But now I'm going from 150 volts to 250 volts. That change is positive. Positive. It's going uphill. Unless I redefine downhill. If I call this downhill, if I say downhill is the direction towards lower potential energy, then everything falls downhill. Everything falls to a state of lower potential energy. Because that's how it speeds up, is it takes that potential energy and turns it into kinetic energy. See if your neighbor understands down. Down. What you get off a duck?
Seem to
Like, sort of going up.
The negative.
Correct, if it goes.
Okay. Now, how did I get this high voltage and this low voltage? Well, I could do it with a positive plate up here and a negative plate down there. And I'm always going to have a higher voltage near the positive plate and a lower voltage near the negative plate. Okay. And you see that this positive charge is going to want to race towards the negative plate. This negative charge is going to want to race towards the positive plate. Okay. Clicker question. This is problem 1 in homework 10. Point A is at an electric voltage of 750 volts. B is at an electric voltage of 950 volts. An electron is observed moving at some speed at A. When we observe it at B, the electron speed will have increased, decreased, or stayed the same. Let me get you started. Okay, now you can click.
Higher, so now going down half negative. That's the electron. Along with those things. Have increased. Yeah, just a higher speed.
If it's electron, it's going from 7 to speed.
Okay, last call, get your vote in. Get your clicker points. Good, the answer is A. The answer is A. Well, let's see why it's A, okay? The change in voltage, that's easy. You're going from 750 volts to 950. If that were money, you'd say, woo-hoo, I'm happy, okay? That's gonna be positive. But that's not what I care about. That's just a gimmick to get me what I really care about. What I really care about is the change in the electric potential energy bucket. Is that positive or negative? Well, remember, that's equal to the change in voltage. That's positive. But I have to multiply by the test charge that's going from A to B. That's negative. And a negative times a positive is going to give me a negative value. That means the potential energy bucket is draining. And that means it's a zero-sum game. The kinetic energy bucket is filling. And that means I'm speeding up. I'm getting more kinetic energy, so the speed is increased. Okay, questions on that? That's how we play the game. That's how we play the game. Now, there's one more huge idea that you need for your homework, and that is this. It's very quick. If I measure the voltage difference from A to B and find it some value V naught, something, 50 volts, okay? If I somehow double the field between those plates so that now I'm fighting a field that's twice as strong as I bring that charge from A to B, what's going to happen to my voltage between A and B? Shout it out. It'll double. It'll double. Okay, hold that thought. Now, if I go back to the original field, but I move the 2 points closer together, so they're half as far apart, what does that do to the voltage between A and B? Remember, the voltage is how much Verk I have to do to bring 1 coulomb from A to B. I still have to push like I did before, but only half as far. How much Verk am I doing? Half as much, okay? Let's put that together, okay? How do I find the change in voltage from A to B, given the fact that I know what E is and I know what D is? Well, let's do the math. I know that the Verk that I do is going to change all of the energy. But if I move this test charge, doesn't have to be 1 coulomb now. I am going to ask that it be positive, okay? So that I'm doing positive Verk. Now, if I move that test charge from rest at A to rest at B, I don't change my kinetic energy bucket. And so I can find out how much I fill up the electric potential bucket by looking at how much Verk I do. Now, the electric potential energy bucket is just the test charge times the voltage difference from A to B. And that's what I'm looking for. I'm looking for a formula for voltage difference. Well, the Verk is just going to be the force that I exert with the hand times the distance that I push for. Well, how hard do I have to push with the hand? Well, let's look at a free body diagram. I have the electric force And that's just going to be the test charge times the electric field. If I want to move this at a slow, constant velocity, zero acceleration, I have to push exactly this hard. I want this diagram to scream balance. And so if I plug that in for the force by the hand, Q test times E, and I cancel out the Q test, I get the formula I'm looking for. And I don't think any of you are old enough to get this. I'll see.
You're getting it right from the horse's mouth.
Who's that? Mr. Ed, this is the Ed equation, the Ed equation. Mr. Ed was a talking horse. You don't know that? Okay, wait. A warning. This Ed equation is so simple, you're going to want to use it for everything. This is going to be your tool of choice. But it has yellow caution tape around it. Warning, warning. Don't even think of using the Ed equation unless your electric field is uniform. What does that mean? It means that your field lines are parallel. That's what you get in between two charge plates or near one charge plate. But don't go using it around a point source or something that has field lines that are spreading out. Okay? Now, this is Mr. Ed, the talking horse, and he would only talk to Wilbur. A horse is a horse, of course. I mean, you just don't understand. They made him talk by shoving a whole bunch of peanut butter in his mouth, and then he would just try to get the peanut butter off of his teeth, and it looked like he was talking. It was like waterboarding for horses, and it was torture, and it wouldn't be allowed today. But it was a very popular show when I was alive. Okay? That's where the other class got to this morning, so why don't you go somewhere else? A blessing on your head.
The Lord is.